Hi, I'm Julian Morgan, and I'm here to kick off the presentation of Northeastern University's entry into the 2020 Big Idea Challenge, the surveying craft for observing unexplored terrain and deployable out-of-crater generator for holding and utilizing solar energy, also known as Scout and Doghouse. First, I'm going to talk about the design decision and system overview. To start off, our team identified key challenges for a PSR mobility system, first of which was data preservation. Because a mobility system within a crater does not keep line of sight with the lander, it creates the risk of data loss. Additionally, that limits the exploration range because the rover needs to return to the crater's edge to transmit data. Another issue that we identified was the inability to collect energy while exploring. This causes charging downtime. As the rover sits on the crater's edge collecting energy, it is limited by the solar panel's transfer rate to the charger, and that creates a bottleneck where the rover cannot explore and simply needs to sit and collect energy. In the actual exploration process, unknown soil properties create an increased risk of the rover getting trapped. A mobility system would need adaptability to different soil textures and be able to navigate both the abrasive, regolith, and be able to adjust to different levels of porosity in the soil. Finally, our team identified that navigating without light would pose significant challenges for a rover of this size. It would be too costly to generate its own light on the energy budget, and it would be too difficult to reflect light in from the crater's edge that would rely on heavy infrastructure that is not present at this time. So, here's our original plan. Scout would be a quadrupedal exploration system that would deploy from the lander, walk to the crater's edge, drop Doghouse, and then make excursions into the crater. It would return to Doghouse, which would serve as a relay station. Doghouse would sit on the crater's edge, passively collecting energy and transmitting data to the lander. This two-step system also preserves line of sight, and the quadrupedal nature of Scout allows for more adaptability in the unknown soil. Scout would contain a communications array, a LiDAR scanner, and wireless charging. Doghouse would also contain wireless charging and communication, and both would contain significant batteries that allow the wireless chargers to quickly transfer data rather than Scout needing to collect its own data and wasting that time on downtime. The current build state of the project. Scout Lite is a stand-in system that was built instead of Scout because of the timeline cuts that the system had to face. Scout Lite is essentially the electoral box for Scout Lite. It includes wireless charging and LiDAR scanner, and additionally the onboard computing. It does not include the quadrupedal legged system because our team determined that was outside of the scope given the changes that we had to make due to coronavirus. Doghouse with the relay station is partially assembled with the main internals built, but the solar panel array not yet complete due to timeline cuts due to coronavirus. That said, it is able to rotate the solar panel array, and the solar panel array is able to deploy, and the deployment mechanism currently works. But I'll let members of our mechanical team get into the details there later. First off, one of our mechanical leads, Belen Wu, will talk about the designs behind Scout Lite.
The final mobility system that was built, Scout Lite, was developed for the purpose of integrating and testing Scout's original sensing, communication, and wireless charging capabilities. Scout Lite works in conjunction with the support module Doghouse, which is used for communication and charging. The system leaves Doghouse after wirelessly charging up its batteries and begins traveling to explore and map out unknown terrain. Scout Lite at this point in time can travel down coded paths and stop to map upcoming terrain. Through simulation software, Scout Lite can utilize scanned images to plan out paths for future movements. The system itself consists of 4 brushed DC motors mounted on Scout's original carbon fiber electrical box. This shows that the system's electronics are capable of fitting in their allocated space. The motors are connected to omnidirectional wheels for easy multi-directional movement and rotation, similar to that of a legged system. Scout Lite's contained subsystems consist of a wireless charging coil used to charge the system when connected to its support module Doghouse, LiDAR equipment capable of scanning and mapping out Scout Lite's travel paths, and IR equipment to facilitate the communication of data between Scout Lite and Doghouse.
Next up is another one of our mechanical leads, Paige Butler, as well as Lindsay Houston to talk about the designs behind Doghouse.
Doghouse is a relay station between the lander and Scout, which ensures line of sight is held continuously during the mission. After Scout deploys Doghouse on the edge of a crater, the spring driving system will deploy the solar panels, allowing Scout to begin recharging its batteries to then begin PSR exploration. Doghouse will then transmit data from Scout to the lander. The rotating mechanism will rotate the solar panels throughout the mission in accordance with the sun, ensuring that power is continuously converted at max efficiency. Doghouse consists of an electrical box containing the components necessary for wireless charging and IR communications to Scout, as well as the solar panel deployment mechanism's spring driving system and rotation mechanism. The solar panels and telescoping rods themselves are attached to the top surface of the electrical box.
We designed a folding solar panel framework to hold the high-efficiency multi-junction solar cells developed by Glenn Research Center. We then designed a deployment mechanism that will allow the solar panels to extend from a stored folded position in order to receive sunlight. The framework of panels is designed to be deployed using a car antenna-like mechanism that extends the rods connected to the solar panel framework. The panels were designed to stow within the space allotted within the lander. Unfortunately, the connection between the frames and the rods was not able to be fully constructed. A lightweight bevel gear assembly connects a motor inside the electrical box to a thin piece of carbon fiber that the solar panel rests on. When the motor turns, the solar panel assembly turns, allowing the panels to always adjust to face the sun. In the current build, electrical problems inhibited the motor from functioning properly. However, the mechanical design was verified. A 3D printed base, reinforced with carbon fiber, contains all of the electrical components for Doghouse system. This box was designed with the size constraints of the mission in mind and proves that all of the necessary components to make the system function can be contained within it. The battery within Doghouse successfully outputted power through the wireless charging coil.
Next up, we'll talk about some of the critical subsystems present within Scout and Doghouse. First up is wireless charging with our electrical lead Ganesh Kohli.
Most spacecraft systems are unitary, with electrical processes self-contained within the vehicle. The unique modular setup of our design allows for a surveying and sensing rover in Scout Light, as well as a power and communications relay station in Doghouse. However, with this more flexible organization, power management is split into these two systems. Smaller rover systems such as Scout Light are not large enough to carry dedicated power supplies, limiting mobility if tethered. To accomplish power transmission, conventional wired charging will prove to be difficult in the unforgiving lunar environment, as exhibited in the image below. This is due to the jagged regolith blocking the ports, inhibiting a proper connection. There's another challenge in positioning both systems to correct orientations for proper charging to take place. Harsh temperatures may also damage external facing equipment, such as charging ports. As there's no light in the PSRs, solar-powered spacecraft cannot withstand the 14-day lunar night, and other forms of power generation, transmission, and distribution must be used. This is solved with the use of wireless charging, utilized to transfer power from the Doghouse to Scout Light systems through the use of custom coils and battery management systems. A 200-watt transmitter was placed on Doghouse, which would transfer power to the 200-watt receiver placed on Scout Light. The actual output of the transmitter was 154 watts. While the maximum power budget of Scout Light is 164 watts, this value is not reached as the system is never running all processes at 100% capacity. To match the battery cell configuration of Scout Light, the transmitter output was set to 22 volts. To properly align the two coils, a conical indent on the Doghouse side and a matching extrusion on the Scout Light side allowed the two coils to match when pairing. Below are images of the wireless charging receiving coil on the right, as well as its placement on Scout Light, left. The images on the left and bottom display the wireless charging transfer of power from Doghouse to Scout Light, with their power management systems attached. Current is discharged from 5.5 amps before leveling to 3.87 amps, for a minimum efficiency of 75%. Various positions between coils for power transfer were tested, as viewed in the table to the right. If the optimal position is not reached, a voltage regulator is utilized to maintain constant voltage output for transfer. We consistently achieved an average voltage efficiency rate of 86%, which is higher than conventional wireless charging systems, which have efficiency between 75 and 80%. At a discharge rate of 4.86 amps, the temperature of the system due to heat dissipated was between 22.6 and 45.2 degrees Celsius, which can be removed by adding radiators to expel the heat. Wireless charging proved to be successful in our design and proves its efficacy within modular systems for future space missions.
Next up is electrical simulation with one of our electrical members, Dylan Gates.
Our electrical simulations of both Doghouse and Scout Light consisted of a three-step process where we first had to generate basic concepts for each subsystem by including all the components and connections. naming and listing all dependencies of every subsystem, and then lastly include the main components of each subsystem. We would then start building the list of subsystems individually under Simscape and Simulink, where Simscape was used purely for electrical simulation and Simulink helped with graphing out the logic behind these subsystems. Lastly, we would connect the individual components of every subsystem to verify if the simulation's data and outputs match with our predictions prior. We, as a team, chose this route to create a simulation design in this project since we needed an environment to simulate our key mission objectives as we didn't have access to our labs to do physical prototyping before September. With the help of our advisor, Professor Ramazani, we were able to use the software as a proof of concept of several mission-critical objectives for us, such as navigation capabilities, the Scout Light and Doghouse subsystem communications, and producing a LiDAR scanning model. As of now, we were able to get a lab space which made it possible for us to verify our physical components capabilities with their simulation results. The next two slides show an electrical block diagrams of Scout Light and Doghouse, and these schematic documents help with matching the arrangement of the components for both systems. Our main objective was to simulate Doghouse and Scout Light's entire platforms. The next two slides show electrical block diagrams of Scout Light and Doghouse, and these schematic documents help with matching the arrangements of all the components from both systems. As our main objective was to simulate Doghouse and Scout Light's entire platforms, we did highlight a few specific systems, such as the low-power IR, the wireless charging system, and the motors, to focus more on correcting their power connections and communications throughout the entire system. Now for Doghouse to communicate to Scout Light with the IR receiver, you need to make sure that the Wi-Fi dongle and the IR PCB will be receiving power and signals from the main computer, which is a Raspberry Pi 4, so that our lander will receive a low-power route of communication as the Scout Light is being wirelessly charged in the crater. After detailing how each component in Doghouse and Scout Light connects with each other, we implemented our ideas into Simulink, where our final simulation design has a low and high power IR signal receiver connecting from Doghouse to Scout Light, just to discuss in the block diagrams before. The high power IR communicates with all the scans coming from the LiDAR, while the low power IR controls signals that both Scout Light and Doghouse are transferring and receiving from each other, while Scout Light is either in motion or stationary. In the Simulink scope outputs, you can see that the rate of signal power, the voltage, and the current is being transmitted from the Doghouse and being received from Scout Light, as discussed before.
Now, we'll delve into our navigation system with our controls lead, Julia Obelhija, as well as Andres Zonis and Lindsay Riggs.
Our navigation system can be thought of in three distinct parts. First, we do data collection to view our environment. Second, we do map generation and generate a map based off of the data that we've taken in. And third, we do pathfinding, which allows us to create a path for our robot to follow through the map that we generated.
Data collection is done via LiDAR scanning. We knew low light conditions eliminated stereophotography as a possibility unless light was somehow created, which would have had high power costs. Using LiDAR technology, we can map in full darkness, as long as the map surfaces do not absorb infrared light, which we have no indication that lunar regolith does. The scanner's hardware consists of two rotation stages for horizontal and vertical movement. The upper rotation stage consists of a LiDAR scanner and a stepper motor, while the lower rotation stage consists of a microcontroller, a quadrature encoder, a DC motor, and the geared system. The use of a LiDAR unit for scanning allows mapping to be done in low-light environments such as a PSR.
Our system was capable of taking up to 750,000 data points per minute, with full scans taking between 2 and 7 minutes depending on their required fidelity. We did experience some tearing between values at long distances on flat terrain, as shown in Scan 1 taken in a field. However, up close they were much clearer, as taken in the Scan 2, which was taken indoors. As for path to flight, the system should be tested against lunar regolith to verify that the signals will not be absorbed by the material. We have no reason to believe that they will be, but we should still verify. As for reducing the tearing at long distances, higher resolution encoders would reduce the distance between data values, which would produce more navigable maps and allow the rover to travel farther between scans.
LiDAR scans are taken in, then mapped using the Hector mapping package for ROS. This uses a simultaneous localization and mapping approach, which is a way of mapping an environment while concurrently determining the position of the robot. This method creates a 2- or 3-dimensional map that is then converted into an occupancy grid. We decided on using a 2-dimensional map for the sake of information storage space and communication load. However, we felt that 3-dimensional maps stored in occupancy grids are an underutilized technology. These can be used in future missions where we are interested in exploring confined spaces such as caves and lava tubes. The occupancy grids obtained from the LiDAR data are then used for pathfinding.
The final challenge that we needed to solve was how to pathfind, how to take this map that we had created and use it to create a path for our robot to follow. In order to do this, we needed to decide what pathfinding algorithm would be best to use. To pick an algorithm, we needed to satisfy a few of our desired goals. Our current system works by our robot stopping, doing a scan, generating a map, and then pathfinding through it. That works for now, but if in the future we want to be able to do continuous pathfinding as the robot is traveling, we need an algorithm that can support both static pathfinding and live pathfinding. In order to do this, we selected the D-Star Light pathfinding algorithm. Let me take you through an example of how the D-Star Light path planning works. So the image you see here is an example of one of these 2D occupancy grids. It's not what is actually being used, but for the purposes of illustrating how our path planning works, it will suffice. At the top left corner, you see a green square. This marks our starting point. In the bottom right, you'll see a pink square. This is our goal point. The first thing that the D-Star Light path planning algorithm will do is calculate the shortest path between these 2 points. And that's what you can see here in the blue. Once we have this path generated, it's very easy for the robot to follow it. However, what's really important, and the reason we chose the D-Star Light path planning algorithm, is its ability to do path replanning. This is illustrated when we add obstacles. The squares in yellow are new obstacles that we've added, and you can see the path in the bottom right changes slightly. To illustrate this, I'll go back to the former path. It moves down a little bit. Because this isn't a huge change, let's add another obstacle for a little bit more clarity. With another obstacle, the path changes significantly to find the most efficient way for the robot to get to the target. This ability to do consistent replanning would be instrumental if we wanted to create a scenario in which our robot did live path planning. Through the course of our testing, we are able to create reasonable expectations for how long we think pathfinding will take us. It's a very linear relationship between the time it takes to create that first shortest path, the line in blue that you saw earlier, and the actual amount of squares that we're planning through, the grid size. This makes sense. The larger the amount of area we have to plan through, the longer it takes to do so. We found that for the grid size that we plan on taking in, it will take us no more than 679 milliseconds to plan through it. This is just over half of a second, or very reasonable for us to manage time-wise. Things get a little bit more interesting when we look at the time it takes to do path replanning. This is a non-linear relationship between the size of the total grid and the amount of time it takes to do each of those path replans. This is because we are not replanning over the entire grid, instead a small localized area. This area size depends greatly on how many new obstacles have been added and the total original obstacles in that area. We anticipate that for the purposes of the types of replanning that we'll be doing, we won't see path replanning taking us longer than 10 milliseconds, and on average around 5 to 6 milliseconds. This has all been informed by the testing that we've done. This is an extremely efficient rate, and we are convinced that this will allow us to do efficient path replanning as needed. For these reasons, we feel we have built a robust navigational system that allows us to take in data, generate a map based on that data, and pathfind efficiently through that data.
Now we'll talk about our infrared communication system with Jake Trimble, Javier Coindro, and Kyle Tobias.
The LiDAR scans produced by the navigation system also pass to our communications protocol, where software packages data into individual packets of up to 2 kilobytes in length. When these packets are received, they are reassembled by the same system back into complete data objects. This program is also responsible for keeping track of missing and/or malformed packets and emitting resend requests when these are detected, as well as acknowledging the receipt of incoming data. Because the data produced by the LiDAR system is very large, we have to perform some form of compression in order to reduce transfer times and lower the risk of errors. The nature of the LiDAR data means that it is suited to run-length encoding, which shortens sequences of identical data to small tokens, as can be seen in this diagram. Our implementation of the algorithm was able to compress our sample data by over 14,000 times. Because this was determined using sample data, real-life scans may not compress as efficiently. After the data is compressed and split into packets, it is sent over serial to our transmission software.
Our priorities while developing the transmission system for Scout and Dockhouse was to have a very high bandwidth compared to the power that was being consumed, and to have a decent range large enough to fit our needs. From these priorities, we decided to develop an infrared transmission system, which is pretty novel in the space exploration realm, that consists of two separate elements. One would be a high bandwidth transmission system meant for transmitting LiDAR scans and maps, and the other one would be low bandwidth meant for transmitting battery data, diagnostics, and Scout's position. This system would allow for both flexibility, because based off of the data size, we would be able to take a different route that was optimized for this, and redundancy, because if any one of the systems were to fail or lose connection, the other one could take its place. Our priority with this was to lower retransmission as much as possible. While developing the system, we did some experimentation and realized that from the bandwidth at which the first errors start to appear in transmission, to the bandwidth at which the errors are unrecoverable, it almost doubled the initial bandwidth, meaning that if we did not have some error correction system, we would be losing effectively 75% of our total bandwidth range. So we focused on error correction, specifically Reed-Solomon error correction, and determined that a 25% overhead would allow a more than 50% drop in retransmission at these higher bandwidths, which would both notably improve our effective bandwidth and allow us to transmit higher quality data at higher rates. We specifically decided to write our own allocation-free Reed-Solomon encoding on our microcontroller for performance reasons. This system can deal with both single-bit and continuous errors. A great example is here on the right with this image of the Mona Lisa. They're using a 2/3 Reed-Solomon encoding while we are using a 3/4. That's how much of the total data is actual data and not error correction. But you can still see that very corrupted image on the left, with straight lines going down, which are continuous errors, and individual dots, which are single-bit errors, are corrected perfectly on the right.
As we mentioned, the infrared communication system is split into two PCBs, capable of processing IR data in high and low frequency bandwidths. The high-power PCB was designed using a photodiode and the most crucial stage, a transimpedance amplifier stage, which contains an active high-pass filter that filters out frequencies below 100 kHz, diodes that prevent saturation, and has a gain of 35 megavolts per amp. The low-power PCB both receives and transmits infrared data at 38 kHz and utilizes a transceiver and UART chip to transmit, receive, and process data. The transceiver is an IRDA 2.1 compatible chip that operates while comfortably processing 2.4 kilobits per second to 115.2 kilobits per second and operates from 3 volts to 5 volts. It processes data from an IR receiver into usable CMOS output levels. The Universal Asynchronous Receiver Transmitter chip uses CMOS data to control the IR transmitter pulses and operates comfortably between 2.7 volts and 5.5 volts.
Finally, we'll wrap up with our solar panel deployment mechanism with Paige Butler and Matt Schroeder.
The deployment system was designed to utilize Glenn Research Center's high-efficiency multi-junction solar cells, which have a conversion efficiency of 30 to over 40%. A 0.5 square meter array of these cells would allow us to recharge Scout as needed throughout the mission. The connection between these solar panels and the telescoping rods was designed to fit into the underside of Scout so that longer telescoping rods could be used without increasing the total stowed height.
The telescoping rods subsystem consists of 10 stacked carbon fiber rods. When collapsed, they stand at a height of 0.2 meters, and when fully extended, they reach a height of 1.5 meters. To keep the telescoping rods extended, a locking mechanism is used that consists of 4 pins that are pressed into slots at the bottom of the rod, which prevents the rod from falling back down. In the diagram at the bottom with the red pin, our intention of using a compression spring is shown, which would push the pin into the slot once the telescoping rod reached the correct height. However, to make prototyping simpler, we utilize rubber bands in place of the compression springs to push the pins into the slots.
Although many deployment types were considered, for the solar panels, a spring-powered system, similar to a car antenna mechanism, was decided upon. This is due to its low power consumption, its large stored-to-deployment height ratio of 7.5, and its significantly lower mass as it did not utilize a motor. The 8 telescoping rods and the solar panel frames were made of carbon fiber to maintain rigidity while deployed, while also minimizing overall mass.
This diagram is a cross-section of the spring driving mechanism. In the center, there are 3 torque springs inside of a 3D printed housing. These springs are coiled up, and when released, they turn a driving gear, which meshes with a flexible gear rack. This flexible gear rack is connected to the top of the telescoping rods and is driven upwards by the driving gear, which extends the telescoping rods and unfolds the solar panels to a height of 1.5 meters. The flexible gear rack is initially coiled 9 times inside of its own 3D printed housing, which includes a guide that reduces friction and enables meshing of the gear rack with the driving gear without jamming. The springs would be coiled up prior to launch, and their tension would be released with a solenoid located in the back. Now I will describe the solar panel deployment testing results. For the spring driving mechanism, we were able to drive 1.5 meters of the flexible gear rack out of its housing. This test was successfully repeated more than 15 times. We were also able to use the solenoid to automatically release the spring mechanism and launch the flexible gear rack. The telescoping rods were constructed and the locking mechanism was mechanically verified. Our progress with integrating the 2 systems can be seen in the videos on the left. We were able to utilize the spring driving mechanism to expand the telescoping rods and lock sections of the rods as well.
Now we'll talk about some of the future applications of the systems used within Scout and Doghouse. Within an Artemis application, Doghouse would potentially serve as a support structure for other devices and rovers, and wireless charging allows for a modular approach. Additionally, solar panel deployment mechanism is alternative designed for deployment in low gravity. Finally, LiDAR applications outside of space exploration include automated search and rescue in low light, as well as autonomous vehicle navigation. And finally, on behalf of the entire Northeastern Big Idea team, I'd like to offer a brief thanks. We would not have been able to gain the experience and investigate any of these ideas without the trust of NIA and the folks at NASA. Despite many challenges, we are better engineers, better scientists, and better people for having participated in this competition. So thank you.